We're now going to very briefly consider a couple different types of capacitor structures. The first is a coaxial capacitor, aka a coax cable. And of course, this is important to talk about because a lot of signals are transmitted via coax cables. And so the basic structure is shown here. So we're essentially looking at a cross section. We have an inner conductor and an outer conductor, which are separated by some dielectric. And so typically you'll be sending the signal on the inner conductor while having the outer conductor grounded to help with shielding and to maintain signal integrity. So let's say for this, our coaxial capacitor shown here, we have some inner radius of this inner conductor, which is A, and the radius from the center to our outer conductor is B. So we have some width of our dielectric then, which is going to be B minus A. So if that's the case, the capacitance of our coaxial capacitor is going to be C is equal to 2 pi over epsilon L divided by natural log of B over A, and that capital L in the numerator is the length of our cable. So this is for length L of our coaxial cable. Now, we could go through and we could of course solve this either of the two ways that we've talked about before. We could assume charge on the plates. In this case, of course, we have an inner and an outer. Or we could assume a voltage across the plates and we could find the charge. Just because we have so much other stuff to get to in this class, I don't want to go through that again, the same way we did with our parallel plate capacitor. But if you want to see details about that, you can look on page 253. So another type of configuration, which we're also just briefly going to talk about, is a spherical capacitor. And so with a spherical capacitor, what we have are two concentric spheres, two concentric conducting spheres. So let's write this out. So we have two concentric, and so that just means one is inside of the other, both centered on the same place. So two concentric spherical conductors. And then in between them, we have a dielectric layer. So with a dielectric in between. And so let's say we have some for our inner conductor. So inner conductor IC, I'm going to say R is equal to A. So that's the radius of our inner conductor. And the outer conductor is going to have some radius B. And of course, we're going to have B is greater than A. So again, we can use either of our two methods. So we could assume charge on the conductors. And so to see that method, you can look on page 254 in the textbook. Or we could use our boundary value problem method, and we could assume we have some voltage across the plates and then solve for charge. And so that's shown on page 260 of the textbook. Either method, we're going to end up with, of course, the same equation. And in this case, it's going to be 4 pi over epsilon divided by 1 over A minus 1 over B. Now, you might be asking yourself, why would we ever want to deal with a spherical capacitor? What's the practical use of that? Well, one good practical use of that is to calculate an approximation for stray capacitance of equipment. So stray capacitance of equipment. And so this can be done by letting that outer radius B go to infinity. And so if we have an equipment that's roughly the size of a sphere with radius equals to A, then that approximation, so if we let this B go to infinity, this term is going to go away, and then the result is going to be a good approximation of the stray capacitance for that equipment. And again, this A value is just going to be, we're approximating the equipment as a sphere with radius A. So not super accurate, but a good first order approximation.